Calorimetry. This video lecture is going to explain one of the most important topics of Chapter 9, and that is heat experiments called calorimetry. Now, one of the most important concepts in calorimetry is shown on this slide, and that is the concept of an isolated system. No exchange of energy nor matter with the surroundings. And we're going to assume this for our calorimetry experiments. And basically what that means is that, let's look at this picture right here. If you have a chemical reaction here in the red circle, let's say it gives off heat. It's going to give off some heat to these surroundings, and let's say the surroundings are water, and this is like a bomb calorimeter. So all of the heat that was released by the chemical reaction is going to be absorbed by the water. There will be no heat that is going to go outside the square boundary. And that's what we mean by an isolated system. In this case, everything inside the square boundary would be the system, and outside the square boundary would be the surroundings. We're going to say that all the heat stays inside the square boundary. Now, the most important equation for calorimetry is this one right here, describing energy transfers in terms of heat. Now remember, heat is the transfer of energy between two bodies due to a temperature difference. You have heat flowing from hot to cold, and it's given by this equation where Q is heat, N is the number of moles of a substance, C is the specific heat capacity of that substance, and T is the temperature difference between the hot body and the cold body. This is a disorganized transfer of energy, unlike work. Now the signs on Q are very important. When Q is less than 0, that means that the system has lost energy. It's gone from a high energy state to a low energy state, and energy has been released to the outside part of the system, which we'll call the surroundings. Okay, so here this is called exothermic. An exothermic reaction gives off heat. Conversely, an endothermic reaction takes in heat. The system starts out at a lower energy level, and the heat provided by the surroundings bumps it up to a higher energy level, and thus Q is positive. So in a calorimetry experiment, we will have both a negative Q and a positive Q. Think about this. When the system loses energy, so Q for the system is negative, what do you think Q for the surroundings is? Well, it's positive. All of the Q, all of the heat that the system releases is going to be the same amount of heat that the surroundings absorb. And there will be no heat lost outside of the square. We're going to call this an isolated system. So now let me explain to you the different calorimetry experiments. And the first one is very simple. It is heating up a piece of metal and putting it into cold water to determine the specific heat of a metal. Another calorimetry experiment is determining the heat of reaction. So we have two reactants, we mix them together and measure the temperature increase, and that allows us to determine the delta H of a reaction. The final heat experiment is a bomb calorimeter. And here we have a rigid cube and we have a combustible reactant, and it reacts with oxygen, gives off a lot of heat, heats up the water surrounding the bomb, and we get a delta T from this experiment. So those are the three types of calorimetry experiments. One is called a coffee cup calorimeter. That's for determining the specific heat capacity of a metal. You can also use this coffee cup calorimeter to determine delta H of a reaction. And the bomb calorimeter can determine the delta E of reaction. Now let's go back to these equations and try to understand the difference between delta H and delta E. Now remember from the previous lecture on enthalpy, delta H is the same as the heat transfer at constant pressure, whereas delta E is the same as the heat transfer at constant volume. Remember, the first law of thermodynamics is delta E equals Q plus W. Well, at constant volume, there can be no pressure volume work. So W disappears, and that's why you get delta E equals Q sub V. And if we put this in terms of specific heat capacity, we have delta H equals number of moles times specific heat capacity at constant pressure times the temperature change. And delta E equals number of moles times the specific heat capacity at constant volume times the temperature change. Okay, so now I'm going to describe an experiment which is a heat of neutralization reaction. Notice we're going to monitor the temperature. We're going to take some 5% potassium hydroxide and mix it with 5% acetic acid, otherwise known as vinegar. Okay, now these two chemicals mixed together will produce some heat. We'll start out by adding the vinegar, about 100 mils, to this beaker, and you can see the initial temperature, stir it up a little, 22.7 degrees Celsius. Okay, so now we've got the 5% potassium hydroxide, and we're going to mix that with the 5% acetic acid. Initial temperature 22.6, and notice how the temperature rises immediately. This is a neutralization reaction between an acid and a base, and it is exothermic. So from this delta T that we measure, we can then calculate the delta H of the reaction, because this is occurring at constant pressure. As you can see, we're under 1 atmosphere pressure conditions, and there's our final temperature. Okay, now we're going to put some numbers into that calorimetry problem where we added acid to base to get a neutralization reaction and the release of heat. So let's say we added 100 mils of the acid, which was CH3COOH, and its concentration was 0.7 molar. And to that we added 100 mils of KOH, and its concentration was also 0.7 molar, which corresponds to approximately 5%. Now the net reaction is H plus aqueous plus OH minus aqueous goes to H2O liquid, and of course it gives off heat. And the delta H is the heat of neutralization or the heat of reaction, and that's what we're going to try to calculate. We know that it's negative because heat was released and the temperature went up. Some other information that we need for this problem: the delta T is the difference between T final minus T initial, and that for this problem was 3.5 degrees C. Now we're going to assume that the resultant solution is water, so we have 100 mils of solution 1, 100 mils of solution 2, and so the volume of the solution is 200 mils, and for calorimetry problems we need weight, so that is 200 grams because the density of water is 1 gram per milliliter. And then we also need to know the specific heat capacity of the solution. We'll assume it's mostly water, so C of solution is going to be the same as that for water, which is 4.18 joule per gram per degree C. All right, so we mixed the acid and the base together and we got heat. How much heat did we get? Well, we can calculate that. Q of the solution, and that is simply given by Q of solution equals the mass of the solution times the specific heat capacity times the temperature change. So Q of solution then equals 200 grams times 4.18 joule per gram per degree C, and the temperature change was 3.5 degrees C. And so when we multiply all that together, we get 2926 joules. Okay, now what we really want to find is the heat of reaction. This is the heat that was taken up by the solution that we were able to measure with the temperature change, but we want to find the heat that was released by the mixing of H plus and OH minus. Well, we're going to assume that it's an isolated system. That means that all heat is conserved, and the Q of the reaction equals minus Q of the solution. Sorry about the handwriting. So that is going to equal minus 2926 joules. Okay, so that is the heat of reaction. So the last step is then to find the delta H of reaction, and delta H is given as a per molar quantity, joules per mole or kilojoules per mole. So it is going to be the Q of the reaction divided by the moles, not Mn. Okay, now how do we find the moles? We know Q of reaction already, we just calculated it. The moles are going to be the moles of the product or one of the reactants, since it was all a 1-to-1 ratio. OH minus goes to H2O. Okay, so if we find the moles of water, that's going to be the same as the moles of H plus or OH minus. And so that is going to be the volume of one of these. Remember, it was 100 mils, so that's 0.1 liters times its concentration, which is 0.7 moles per liter, and that gives us 0.07 moles. So now the delta H of reaction equals minus 2926 joules divided by 0.07 moles. And this equals minus 41,800 joules per mole. We often express this in kilojoules, so that's minus 41.8 kilojoules per mole. So now we have a pretty good idea about neutralization reactions. But what I'd like to do right now is show you another reaction on acetic acid, vinegar, and now instead of the potassium hydroxide, we're going to mix it with baking soda, which is sodium bicarbonate. Get a big scoop there. And baking soda is a base, acetic acid is an acid, and you expect a neutralization reaction and the temperature to go up like we just saw. So we make the carbon dioxide gas from this neutralization reaction, and notice what happens to the temperature. It's actually getting colder. So I'm going to leave this as a little puzzle for you to think about, why is it actually getting colder? Maybe you can find the answer on the internet. And come talk to me in class, and we can discuss the different factors that are going on in this reaction.